Okay, let's begin. We're starting quantum physics today, and the reading is due on Thursday. I don't want you to fall behind on this next week. So there is reading. You have to read the next chapter. There's a minor correction I made that I posted this morning, but you don't have to. If you have the old one, it's fine. You don't have to download the new one. So we're beginning quantum physics, but first I want to finish up with a little bit of invisible light that we didn't cover, and this gets us into quantum physics because X-rays are a form of invisible light, as are gamma rays, and this has to do with gamma rays and X-rays. So where do I start? I have all these nice images here. Let's start with just some. This is a good one. Okay, we have the lights down a little bit. You look at that picture. Suppose on the midterm, what I did is I put up this picture. And I said, describe it to me. I could do that during the midterm. I could project a picture and then have you tell me what it's all about. Now, you haven't seen this picture before, so it might be a little bit hard, but you might guess what it is just by what you know about invisible light. I mean, here you have what I think you can identify as somebody's feet. There they are, 2 feet. There are the legs. Looks like there's some sort of clothing on. Notice the clothing is relatively dark. The feet are very bright. Why is that? Well, the feet are glowing. This is a photograph, as I hope you might have guessed, taken in the far infrared. Far infrared 10 to 20 microns, the range in which we are all glowing because we're about 300 Kelvin. So his feet are glowing. Why aren't his pants glowing? Well, the pants aren't as warm as the feet. The idea of the pants is to keep the heat from radiating out. When you generate heat, you put on clothing. That clothing prevents the heat from escaping. It doesn't get radiated. Instead, it gets trapped. Some of it, the inside of the clothing warms up and radiates back to you. It's like the greenhouse effect. The outside of the clothing doesn't warm up because the clothing is an insulator, and the heat doesn't go through the clothing very much. So this is why we wear clothing. Really, we don't do it for the other reason. So so here's the feet. Now he's standing on the floor here. So his feet are warming up the floor. And this floor is cold, and his feet are warm. And the floor underneath him is warm. Isn't that fascinating? Well, here, I'll make it fascinating. Figure out, okay. Ready? Notice where he's warmed up the floor, and the floor is cooling off. But here, where he steps just a little bit, for just an instant, the floor is not quite as warm. And so it's not as bright. But back there it is, but it is fading. Well, you can't really see the fading very well. So this is the far infrared imaging. You can imagine all sorts of uses for this. Boy, you've always wanted to measure people's feet. This is an automobile engine. See where it's glowing? I once had one of these devices. I went out into a parking lot and I looked at the engines. I could tell which cars had recently arrived because they were warmer. I didn't have to open up the hood. You could see on the hood which ones were glowing. Imagine if, you're a policeman or something, and you can tell which car came in most recently because it's still hot. This is the engine. This is also a little movie, and it just scans around. There's a person coming out. There's the hood there's a door opening, and there's somebody in there. And come on out. Get out. Yeah, you. Get out. Well, here we go. We're just looping it again. There's the car. The door is opening. There's someone sitting in there. We're looking from the front. There's the open doors over here. There's the windshield. And he comes out, and his face is glowing, and his clothing is not glowing quite so much because the clothing is not radiating as much because the inside is warm, but the outside isn't. So it doesn't radiate. Serves as like a little mini greenhouse. So this is another far infrared image. Here's an interesting far infrared image. Here they added false color. So to make it more dramatic, to make it easier for the eye to interpret, the bright things were made, well, let me make this bigger, were made red, and the cool things were made blue. And that's not because the camera sees red and blue. The camera doesn't see any color at all. It just measures one thing, the intensity. They add the false colors in the computer simply to make it easier for the eye to interpret. And as you look at this, in fact, what I'm going to do is move this over here, and then I can stay on this side. What do you see? Red is bright. So the windows, lots of energy being radiated out the windows. This is why, if you're worried about insulation, one of the things you do is put in special windows, because a lot of heat will leave through the windows, because the inside of the house is warm. The surface of the house is supposed to be cold. You want the walls of the house to be warm on the inside, cold on the outside. Any insulation in there will keep the heat from the inside to go to the outside, and that way they will radiate back into the inside. So, if you want to save energy, personally, one of the most important things you can do if you happen to have a home that you can change like this is put insulation in the walls. Makes a huge difference. You find you don't have to turn the heat on if you put insulation in the walls. The kind of insulation that people like to put in the walls are things like, well, it used to be asbestos. There's a movie I saw recently that ended with a screen coming down, and it said on it, asbestos. That was the high tech of the 1930s. These days, asbestos is in bad repute. But if you look at this, look, there's heat leaking out there. At the top of this, what is that? Is that a window? That's a door. Heat leaking out at the top of the door. If I took a photo of my house and I saw, oh, that's where I'm losing my heat. Well, no, I'm losing a lot there. But what's this? The very top of the house. Well, the hot air tends to go up. It's accumulating up here in the attic, and so the top is where it's hot. A little bit of insulation up there might do a real lot of good, just preventing that heat from coming out. And you can see it gets cooler as we come down here. The ground is quite cool. Well, the whole house is sort of warm, but that's because some of the heat is coming out through the walls. So this is the sort of technology that can be absolutely valuable if you're trying to conserve energy. In other words, if you're trying to save money. Okay, let's do another one. I have a bunch of interesting photos, each one of which I find really interesting. Oh, this is a street scene. Okay, so just a street scene. These things are on the web. They're done by companies that sell infrared cameras. And they put these up so you can take a look at them and see, do you want to buy one of these infrared cameras? And in this case, it's just a street scene. Again, you can see the windows where it's inside. Those are what's glowing, not because lights are on, but because it's warmer in there. There's several places where it's really warm inside. And here's a person, looks like he's on a bicycle, I guess. Looks like a unicycle from here. I'm not sure I believe that. So, typical street scene. Let's see what else. Oh, this one I like. Remember when I told you about Stinger missiles? Stinger missiles are these handheld missiles that were developed by the United States and, in my mind, mistakenly sold to the Taliban back when they were fighting the Russians. I was horrified at the time. I didn't particularly think the Taliban were going to be really nice allies in the future. But anyway, we sold it to them, and they're hand-carried. And what they do is they have a little infrared sensor in the front. And the little infrared sensor looks for something hot. It's basically divided up into 4 sectors. If the hot is on one side, then as the missile is moving, it changes its fins a little bit and moves in that direction. If now the hot spot's on the other side, it moves back there. It keeps on going until all 4 sectors have the same amount of heat in them. Then it's aimed at the heat. Typically, these are used against airplanes. And people really worried about Baghdad. People worry about the United States, all sorts of things. So here's a little bit of a movie of an airplane. And you can see it's glowing. That's because the sky, the clouds are warm. This is the ground. There's some warm clouds up there. It's going to come behind a building. I'll show you this movie. But there's the airplane coming in. And the airplane is warmer than the sky. Well, that's not surprising. It doesn't have to be very warm to be warmer than the sky. It's not as warm as a human, but they turned up the amplification so that the airplane glows. So let's watch this movie now. So here it's coming in. It was behind the building. It's coming towards us. Now take a look at the back of the engines. You see all this coming out there? See that glowing white stuff out the back of the engines? That's the exhausting fuel. It's not a flame. You've landed in an airplane. You don't see flames shooting out of the back of the engines. Okay, but in the far infrared, it is glowing because it is a hot gas. And that's what the Stinger missile goes for. So let's just look at that again. It was behind the building. It's coming towards us. A little bit of an optical illusion there. And here at the back of is the flame coming out. It's not a flame. It's just hot gas. Okay? Stinger bait. Okay, let's see what else I have here. Oh, this is fun. This is a pan of water. Okay? But not quite so simple. It's a pan of cold water. And now what we're going to do is to pour some hot water into the cold water. Okay, now just watch this. It's, you'll see things, I mean, imagine pouring hot water into cold water, and you watch it and say, what do you see? Well, you see nothing. Right? So let's take a look at this. Water. Here comes the hot water pouring in. It looks like milk, doesn't it? And you see the temperature. You see how it's being stirred. This is really an interesting movie if you're trying to understand, if you care about how water mixes. Okay, whoops. Okay, what else do we have? A lot of things here, but some of them have to do with medical imaging. I'll get to those in a moment. Oh, this I like. This is the refrigerator. Okay. That is a refrigerator. Refrigerators are supposed to keep things cold. They emit the heat in the back. We're not looking at the back, we're looking at the front. There's the refrigerator. Look at that crack between the freezer and the bottom part. That's dark. What does that mean? It means it's extra cold. Why is that extra cold? Well, because the insulation isn't so good. Remember, refrigerators are cold on the inside. If the things on the outside get cold too, and they do that at the crack where they're in close proximity to the inside, some people refer to that as the cold is leaking out. Every bit as valid as saying heat is being drained into the inside from out there. Two ways of looking at it. So there it is. Inside, of course, if we were to open the door, it should be dark because it's cold in there. So why don't I come by and open the door? There I am. I open the door, and it's dark, and I am glowing like crazy. Why is my clothing glowing? Well, the reason is, in order to well, I'm not that fat. We turned up the amplification in order to be able to look inside as best as possible. And so because you've done that, even his clothing now, you've just made it extra, extra bright. Look over here on the wall. See his reflection? The far infrared is bouncing off the wall, and you can see the guy's reflection over here. Just watch it again. As it comes up, you see his reflection in the wall. The wall's acting like a mirror. It bounces the far infrared better than it bounces visible. Of course, maybe you'd see it in the visible too. Okay. These are the invisible light movies. Oh, this one is, now, that's a person's eye. I'm just curious. Stop for a moment without raising your hand or saying anything. I want you to tell me, don't tell me, just think. Is this person male or female? Okay, now without changing your mind, I'm curious how many people think it's male? Curious how many people think it's female? So it's about 3 to 1. I have no idea. But it's really interesting that simply looking at an eye, this shows how tuned animals are to recognizing other animals and details about them that aren't at all evident. Well, of course, maybe you're all wrong, but the fact that I mean, how many people here didn't really want to raise their hands because they had no opinion? Okay, but it's interesting that so many of you had an opinion, and a lot of you were right. I don't know which ones. Okay, so here's the eye. Now you can look at the eye, and you see the lashes look like lashes. That's because they're not carrying blood. They're not warm. It seems to be really warm right around the edge of the eye. Well, of course, you know, you don't have the layer of skin insulation there. You may have teardrops coming. In fact, there's a little cool thing here, which leads me to believe, for reasons you'll understand in a moment, that there's a little bit of water evaporating. We're going to get him or her to blink. When he or she blinks, the eye will be coated with a thin layer of water. That water will start evaporating and will cool. So you'll see a little bit of cooling from the blink. So let's take a look at this. Now what you notice is that there's that layer of cooling, but notice that's moving up. Why is that? Well, that's because the bottom part of the eye is exposed first. So it starts radiating, it starts getting, it evaporates first. It's the first cool part, but then it's only a thin layer of water. And pretty soon it's warmed up by the eye. Up here, and you know, really, you blink a lot because you want to keep on covering the eye with this water. And the cool part moves up because that's where there's enough water to still evaporate up near the top. Now that you've seen him or her blinking, did you change your mind about whether he's a she or she's a he? I don't know. You know, this thing, the people, in my opinion, who seem to understand these subtleties the best, I think, are the cartoonists. They'll make one little line that'll make a cartoon character from being a male into a female or the other way around. Very little subtle things. I'm fascinated with this art. I know some cartoonists. And they have the way of just seeing what is it. I mean, it goes back to the old Disney cartoons when you ask what's the difference between Donald Duck and Daisy Duck. You know the difference is you look at them. Daisy has long eyelashes. That's it. Okay, enough to make Donald fall in love. Okay. So what else do we have here? I guess that's about it. Now, some of these other images are ones I'll show you. This is a particularly fascinating image of the Pentagon. And here's an image of New York City. I don't know how many of you know New York City. I grew up in New York City. Let me move this down a little bit. It's a little bit distracting here. Oops. Okay. There's the Pentagon. There's New York City. See that little park right there? That X is right where I grew up. Deep South Bronx. That's why I'm so tough. I came from the South Bronx. In my adult life, I've only met one person who came from the South Bronx. One other besides me. Lots of people came from the North Bronx. That's where the wealthy people lived. The South Bronx, and that person who also came from the South Bronx, the only other person I've ever met since I got my PhD who came from the South Bronx. So we didn't have very many people. In fact, I went back to my elementary school one time, and they had me give a talk. It came as a surprise, and what really made me sad was when the teacher told the class, see, this shows people from this neighborhood can succeed. Sort of a sad thing to have to say to a class. But anyway, the only other person I've ever met who comes from this neighborhood, who I didn't know at the time, but met subsequently, is Colin Powell. This is the Pentagon, where Powell used to do a lot of his work. Neither of these photographs this is false color, by the way. That's not really the color, because this was not taken in the visible. This is not a satellite photo using visible light. It's using some other kind of light. You all know because you read the chapter. Okay, this likewise. These were taken using radar. Now, radar are microwaves. Microwaves are very low frequency light with very long wavelength. Low frequency, long wavelength go together. Microwaves typically have a wavelength of a centimeter or more, several centimeters. Well, these things are not emitting enough microwaves for you to be able to take a picture, so what they do is the airplane goes over. In this case, it wasn't an airplane, it was a Predator. A Predator is a little unmanned air vehicle. Same thing we use to shoot at Al-Qaeda now. They have a little cannon attached to it. It goes flying around. People, no pilots on it, but the TV is brought back and they see what's there, and then they now have permission, if they see Osama bin Laden, to push the button and fire the missile. It's a Predator. But this Predator was not using visible light. It carried with it radar. In other words, it carried with it a microwave oven with a reflector dish that would send the microwaves out and illuminate the Pentagon. Then the return signal was imaged using a technique that's a little bit more sophisticated than an ordinary camera. In fact, the method that's used is basically mathematically identical to using a hologram. Did you catch that? You're awake, right? Paying attention? That's a yes? Okay. So here we have an image taken in radar. Think about this. It's a radar. It could be taken on a completely black night. And look at it. You can't have that much detail because the wavelength of radar is so large. Remember, you could not, with visible light, you can't see things much smaller than a red blood cell because you're getting down to the wavelength of light. And in radar, you're not going to be able to see something much smaller than a meter because you're getting down to the wavelength of the radar. But look at what you can see. Rather amazing. I don't know if any of you have been to the Pentagon, but this little thing here in the center is what's called a restaurant. And that's where people go, you know. There are restaurants in here, too. They have quite a shopping center inside the Pentagon. But you can go into this thing. It has a cute name. Anybody know the name of that restaurant in there? Nobody? This predates 9/11, goes way, way back when they opened that restaurant. They call it Ground Zero. They call it Ground Zero because they assumed that this was the target spot for a Soviet nuclear missile. Probably right. Anyway, a little perverse humor there, Ground Zero. Okay, let's see. Oh, so, and then this is an image of New York City, also taken, not in this case, I believe, from a satellite. Could have been from, no, I think it was probably a satellite, using radar, using false colors to indicate the intensity of the return. So there's Manhattan, that's Central Park. Empire State Building is about there. Actually, if I point to it with a little pointer here, then the people who are watching this at home, that's where I grew up. That's Central Park. And Empire State Building. This is Brooklyn over here, the Bronx. And this is what's called Long Island. By the way, Long Island is an interesting thing because it was created by the last ice age. When the ice came down from the north, pushing down from the north, it kind of scooped up dirt in front of it. And then it stopped going. When I grew up in the South Bronx here, rocks across the street in the park from where I lived had these big scrapes on them, which were due to the ice scraping them. But Long Island is actually the debris left over from the ice age. When the ice retracted, it left this big pile of dirt that became Long Island. But this is a radar image. This is New Jersey over here. Right over here is where the Sopranos live. So radar imaging, really important technology. It can be used at night. It depends on illuminating the area with microwaves and then getting the return using a hologram-like system to make the image rather than a lens-type system because there are no really good lenses. But it works like a hologram. And no more detail than that because there's no need for us to go into great detail but about a hologram, how a hologram works. It's called synthetic aperture radar, SAR. Synthetic aperture radar, or SAR. It's one of several things that go by the acronym SAR. It is extremely important if you are a president, because many of the images that you get will be radar images rather than visual images. It's a whole new dimension to what you can see. You can see it in absolute darkness. In fact, you see right through clouds because the microwaves go right through clouds. So you should know about this. Let's go to another image now. In fact, let's see what I have here. Okay, this is a typical X-ray image. Now, in X-rays are very high frequency, higher frequency than visible light, shorter wavelength than visible light. They are so high frequency that when they're passing through the atom, most of the electrons, because the electric force goes up and down, up and down, up and down so fast, the electrons don't really respond. And as a result, the X-rays go right through most of the material. Only for heavier elements like calcium and lead, there's lead again, calcium and lead, there's lead, mercury, polonium, all these heavier elements, there the innermost electrons are already vibrating very rapidly because they're going around the atom so fast inside this heavy nucleus. And so the X-rays are stopped by them. So they tend to be stopped by calcium. I want you to know that. By calcium and lead, X-rays don't go through. The way they take this picture, as we've described, is you have a little X-ray emitter. You make an X-ray emitter by having an electron beam hit a piece of material, some heavy metal. That sudden stopping of the electrons, that sudden acceleration creates a wave of high frequency if you stop them fast enough. And so that wave going forward is what we call an X-ray. It's in a wave packet. This is quantum mechanics. We're going to be talking more about this today. It comes in a wave packet, so it looks like a particle of light coming forward. Very high frequency, very energetic, because it had that energy, almost all the energy from the electron. And when it passes through the head, it tends to pass through the brain, not completely, but you don't notice that here because it's mostly the calcium that stops it. So you see the edge here where you're looking through the edge, you're looking through the thick part of the calcium. You look over in the face. So what they do is they have this spot. We have it set up over here. So if we could switch to the X-ray setup over here, the view from the side, you can see what's going on. Yeah, so what we have here, let me see if I can point to it. This laser's a little bit bright. That's the X-ray tube. I'll point up here in this picture. This X-ray tube. What you have in it is an electron beam over here that then hits this plate, creates X-rays that go to, we couldn't get any volunteers from the class, but this teddy bear volunteered to sit there and be X-rayed. So this is a glass tube because it's a vacuum. And then it has a filament that emits electrons. These electrons come off, and they're accelerated in an electric field to several tens of thousands of electron volts of energy. They then hit against that metal. They are stopped suddenly, emit the X-rays, and now what we're going to try to do is I'm going to turn the X-rays on. And if we have again, we have to have all the lights out for this because this is an old display that doesn't work very well anymore. And what is this glow here? Well, that's from that's those lights. Okay. Looking at the shadow to see which way they were coming from. Okay, so what I'm going to do is turn this X-ray thing on. You look at the front here. The X-rays will come through the bear, and we should see the skeleton of the bear. So the room has to be really dark. What's that? Someone, okay. So you may want to focus in. I think this is actually focused in up there on this thing, because it doesn't last very long, I'm told. The tube is getting really old. There it is. Oh, no, what's that up there? Are you looking at the front of the, you should be looking right at this. You're not looking at this because you'd see the laser. So could you focus the camera in on this thing here? Ooh, that's not the camera light. No, I don't mean the light. I mean your camera, so that the people at home. So our video audience. No. I want turn all the lights off, but put the camera and look at this so we can get it for the home audience. Okay? It's hard in the dark to know which switch to push. So let's see. You got it? Yeah, there you go. Okay, so here for the home audience, there is the, let's see how well this comes on. Well, it doesn't show for the home audience, but everybody here can see, especially if you're up close, serves you right for sitting in the back, could see the skeleton of the teddy bear. Okay, that's because the skeleton of the teddy bear in this case was made out of metal. It was a heavy metal. It's absorbing the X-rays. We'd have the lights back on now, please. So where are we? So we're looking at the skeleton here. And when Röntgen discovered this, he thought it was a fraud. I mean, now, he didn't think it was a fraud. Everybody else thought it was a fraud. You could see broken bones. What a great innovation this was. When I was a kid, I would wiggle my feet. Let's get the TV back on the computer. And I wiggle my feet to get shoes fit with X-rays. X-rays do cause cancer, and so this was quickly made illegal. But, so X-rays, so this is a shadow. X-rays are emitted from a point. They go through the skull, and over here they would have a piece of film. These days they still use film because the doctor likes to see the fine detail. Someday they'll start using CCDs and other electronic imaging devices, but for the most part they're still using film because these imaging devices don't have that really fine resolution. We're going to be getting more and more of this. So they still use big pieces of film. It's just a shadow on the film. The place where the light doesn't go through is not exposed. Black means it was hit with lots of X-rays. It was exposed. This is a negative. White is where it didn't go through. You can see the teeth over here, and the nasal cavity, and the eye cavity, and can't see too much of the brain because the brain doesn't absorb as much. There's a little reflection here that is not, that's not a piece of calcium in his head. That's an artifact. So that's the X-ray. Now you can do the same thing with gamma rays. Gamma rays are more energetic. They will go through calcium. You can also use backscatter X-rays. And there's an image, I don't have it here, backscatter X-ray. When you shine an X-ray on me, the X-rays, some of them will bounce off. When they bounce off, you can make an image of it by using a pinhole camera or something like that. These are called backscatter X-rays. So it's like illuminating something with X-rays and then looking at them. And the backscatter X-ray in the text was used to have this picture of the illegal immigrants behind the surface of a truck. There's some issue about whether it has the right to X-ray a truck if there may be illegal immigrants in it. A serious, I think, ethical, technical question whether you're allowed to X-ray someone without their permission, even if they are illegal. So that's something you can discuss among yourselves. The X-ray doses are quite low, but still there are people who are worried about X-rays. Now, let's go on with this. We'll get into quantum mechanics, don't worry. One of the things you can do is to X-ray something from many, many different directions. Now, this is called tomography. Word you should know. You'll come across it a lot. And it is a technology that was made possible by modern computers. The way it works is as follows. You take an X-ray of my head, maybe from the side. Then you take an X-ray from the front. Then you take it from 45 degrees. Then you take it from above. Then you take it from a zillion different directions, maybe 30 different directions. Now, you can now give this to the doctor, and he looks at this and says, ah, blah, 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 blah. Or you can give it to a computer. What the computer does then is it makes a model of the head. it tries to find the distribution of X-ray absorption within the head, three-dimensional image of the head, that would give these 30 different pictures. That's actually not that hard for the computer to do, but you need a fast computer that can handle all these pictures in great detail. So, for example, if you have a head and all 30 pictures have a bright spot right in the middle, then you know there's only one place that bright spot can be if you see the same bright spot in every direction you look. It has to be in the center of the head. On the other hand, if you see a bright spot there, and then in the picture from the side, the bright spot's over here, then you know it's near the front. So in the computer, they take all these different images, and they try to put together a picture of what's going on in the head. We do that with earthquakes to find out what's going on in the earth. We look at many earthquakes, how they travel through the earth. That's tomography of the earth. From this, we've discovered there's a liquid core, for example, because earthquakes that happen to travel right through the middle don't have any shear component. And so there must be liquid in there. And so this is tomography of the earth, but we can do the same thing with X-rays. Sometimes it's called computer-aided tomography, and abbreviated as CAT. So if you know anybody who's had a CAT scan, that's what it is. Typically X-rays from many different directions. This was very useful to us back when the United States had a new embassy building in Moscow, and stupidly, to save money, decided to let the Soviets build it. So somehow we discovered they put bugs inside, and they were very well hidden. But CAT scans revealed the locations of these bugs. So that part of the building was eventually demolished. Cost us a lot of money to build and demolish it, but I suspect the Soviets spent more money in that building than we did. It was really a magnificent job of bugging a building. Boy, if we were told, go ahead, build a building for the Soviet Union. You do whatever you want. Just build it, we'll move in. What would we do? We would get our best scientists and engineers to go in there and do one hell of a job. Well, that's what they did. So, CAT scan, and you saw the image of the CAT scan. Oh, I didn't show you the image of a CAT scan. Here's an image of a CAT scan. Now look at this. When you look at this, you say, wait a minute, I can see the brain now. That's because this is not the whole CAT scan. What you do with the CAT scan is the computer figures out everything inside and where it is and how bright it is. There's some things inside that are quite dim, like the brain. They absorb very few X-rays, but they do absorb some. Normally you wouldn't see this because you're looking at the skull, and the skull is very bright. But now that this thing is inside the computer, the doctor can now say, okay, give me a slice. I want to see only the material that is halfway through. When you're looking at things that are only halfway through, what will you see? Well, it'll look like a sliced open head. And you'll see the calcium, but you won't see any calcium blocking this because the computer has figured out what's on the inside, and it's only showing you what's on the inside. So you see all sorts of amazing detail, the corpus callosum, all these different parts. You see the convolutions of the brain. Look at that, that's the tongue. Nasal cavities, the eye, all sorts of amazing things. If you're a doctor, you think this is the greatest thing since X-rays, and it was. There's another thing, well, there are a bunch of other things that you can do, and let me go through them. This is medical imaging, and you guys are going to run into medical imaging, and not of yourself. A good friend of mine is having an MRI, just had an MRI. You probably know people who've had CAT scans, but this one is really cute. Let's see, where's the one I'm looking for? Okay, this is called, now, yeah, it looks like someone's just had their head lopped off, But what's happened here is the computer has put in, this again is a computer image based on, in this case, gamma rays that are emanating from the brain. Now the way this is done is the person is given radioactive material that emits gamma rays. In fact, the radioactive material is material that's very short-lived, half-life of maybe 10 minutes. It doesn't emit gamma rays, it emits antimatter called positrons. Positrons are electrons with the opposite charge. They're known as antimatter. We're going to be talking a lot about antimatter in the next few weeks. Antimatter is emitted. Now, this is a nucleus that emits antimatter, emits a positron. Now, antimatter, when it's inside a human, will annihilate with an electron. As soon as it slows down a little bit, there's an electron. It's positively charged. The electron is negatively charged. They're attracted to each other. They annihilate and explode. When that happens, two gamma rays come out. Gamma rays are very energetic waves of light. Shorter wavelength than X-rays, more energetic than X-rays. These gamma rays tend to come out in equal and opposite directions. Now, the positron detector, here's the head. Somewhere in the brain, this is where the radioactivity has gone. You could put this in a chemical that tends to concentrate in the blood. Then, for example, you will know where the blood in the brain is. What happens is this emits two gamma rays. They go out in opposite directions. And so you have a detector over here that picks up this gamma ray, have a detector here that picks up this gamma ray. It knows that somewhere along that line is where the gamma ray came out. I'm sorry, where the positron was. Then it picks up another one. Maybe it picks it up here and up here. It knows somewhere along that line, somewhere along that line. So the computer finds the places where the gamma rays are being emitted by figuring out where these lines converge. Again, this is a neat computer problem, not something you'd like to do by hand. Although you could get a pretty good idea. If you have one bright spot, you could probably locate it by hand by doing these kind of measurements. If you have many bright spots, you like to leave it to the computer. So that's what the computer did. It found the bright spots in the brain. This is called positron emission. Tomography. And now I have to confess, the medical researchers really outdid themselves. This was a CAT scan. This thing becomes a PET scan. Uses antimatter. These are done routinely in hospitals. Sometimes people ask me, is antimatter real? Why is it real? It's a tool being used in hospitals to do PET scans. That's about as real as you can get. And it's made possible by the fact there are some radioactive nuclei that, when they explode, emit a positron. So you give the patient that chemical, it goes to part of the brain, and you can then make a map of the brain in false colors, as we show up there, showing which parts of the brain are active, which parts are inactive. A doctor looking at that who's experienced would say something like, oh, that's a real smart person. Or, I got to operate here. Or something like that. I have no idea. Oh, this is cute. This is positron emission tomography being used for research. So here it is, looking at the activity of the brain, presumably the blood, when the person is doing different tasks. Look at this. Look at that really good. Stare at it. Look around. What do you see? Meanwhile, they're watching the brain, and the activity of the brain is concentrated right here behind the eyes. Or is this the back of the head? I'm not sure. I think it may be the back of the head, but that's where the visual part is really active. When you're listening, they see this part of the brain lighting up. So they can look at the part of the brain that has blood going to it. Did you realize that when you're looking at something versus listening to music, that the blood in your brain is being redistributed to go to different parts, the parts that need it the most? For people who can't You know, if you're trying to study while listening to music and really trying to listen to the music and really trying to study, your brain is all confused. Where does the blood go? Anyway, so this is a little bit of research that comes from using the positron emission tomography, the PET scan, to monitor where the activity of the brain is. Now, I have a few other things here. This all goes under the rubric of, perhaps the most dramatic one, though, comes from MRI. So a little story here for MRI. So did I turn this thing off? I want to make sure I turned it off. It's in its dying throes anyway. I'll make sure I turned it off. In MRI, you have the head again. And you don't put anything into the head. What you do is you put the head in a magnetic field. Put it in a strong magnetic field. So I'll draw the magnetic field as if it's a bunch of lines. So typically, someone who's having an MRI scan is put inside of a big magnet. Some people are scared by this, because the magnet may be a huge tube with an opening that's just sort of coffin-like shaped, and you get into this thing and you go inside of this thing, and some people get freaked out. But it's a strong magnet, often using superconducting wire. We'll talk about superconductors shortly. In this strong magnetic field, remember, each one of your electrons is a little magnet, and it's spinning. The magnetic field puts a force on these electrons and causes them to, actually in this case, it's not the electrons, it's the nuclei. They're also little magnets. They're also spinning. And they tend to line up with the magnetic field. Now, in MRI, you use the magnet to get the nuclei to line up. And then what you do is you apply a radio signal to detect those nuclei. And by having the magnetic field be sensitive to only one region at a time, you can make a scan. This is a more complex technology than anything I've told you about. So let me not go into the detail of how that scan is made. What I want you to know is that primarily what you're picking up are protons, which are the nucleus of hydrogen. What they do is, in the magnetic field, these protons will tend to have this force on them from the magnetic field. They wind up precessing in circles at a certain frequency. You then change the magnetic field for different locations. You send in radio waves to excite them into this, to pick up this frequency of precession, as it's called. And then you have radio receivers that pick this up. I'm not going to ask you to describe this in an essay. What I want you to know about MRI is it uses a strong magnetic field and radio waves to detect the presence of hydrogen. That's what you need to know. It can map out the hydrogen. Now, why hydrogen? Well, because hydrogen is easy to detect. Why is that important? Well, hydrogen is in hydrocarbons, and so you have a chance here of measuring something in detail that X-rays are less sensitive to, the hydrocarbons and water. So what would you see if you mapped out the hydrogen? Now, again, this is done on the computer. You map out the entire three-dimensional region of the brain. The doctor then goes up to the computer and says, okay, I would like a slice 8 centimeters in and see what the hydrogen distribution is at that depth. This is called MRI for magnetic, that's the magnet, resonance. That's the fact that these things are oscillating around at a certain frequency that enables you to locate where they are. Imaging. The resonance here, this moving around, is taking place in the nuclei. So here's an important point you need to know. Because it's the nuclei, the proton of the hydrogen, that's undergoing this oscillation, the obvious name for this was nuclear magnetic resonance. resonance. And that was fine. Edward Purcell got a Nobel Prize for his discovery of nuclear magnetic resonance. Turned out to be really important in physics. But now, far more important in medicine. Still important in physics, but somehow people are more important than discoveries, I guess. And so they started using nuclear magnetic resonance. Well, there were dying patients who would not go into the hospital for nuclear magnetic resonance. Anything nuke was something that they had been taught by their favorite fearmonger is something they should be afraid of. So they are here dying of cancer, and they don't want to be nuked. Now you notice no radioactivity was put in. There's some magnetism and some radio waves, but there's nothing radioactive. It's just that it happens to be the hydrogen nucleus that's being detected. Well, you can explain that to anybody in this class, and you say, oh, okay. But to most people, they don't want the doctor, they don't trust the doctor enough. They refuse to do it. So finally, the medical community decided to change the name to magnetic resonance imaging, emphasizing the magnetism. These days, people wear magnets on their shoes to make them feel good. Magnets are good things. Resonance imaging. So NMR, I want you to know this. This was called NMR. It's now called MRI. And the only difference is in the public fear of nukes. So let's go back to the computer, and I will show you an MRI image. Let's see if I can find that here. Gasp. Look at that. This is one of the miracles of modern physics medical technology. If I showed you that and you'd never seen an MRI image, you would have sworn that someone had dissected a human. Look at the detail in that. And the doctor, by turning a knob, can look at a different slice and go right through. This is by far the best way to detect anomalies in the brain. Just a wonderful, wonderful technology. Last few things in here I include just for completeness. This could have been done with a far infrared. In fact, I think it was, now that I think about it. Looking at someone's hands using false color. Sometimes they do this by painting things on the hands, but this is, I believe, done in the false infrared, and I mean the far infrared. And if you look at it, look at the person's two hands, and what do you see? You see some glowing things at the end of the fingertips. You know, is that where I really radiate more of my heat from the ends of my fingers? Very interesting. Probably because there's a high density of blood in there because of the exquisite nerve system we have at the fingertips to give us a delicate sense of touch. I don't know if you've ever done this experiment, but you know, touch your fingers together and think of what a fine thing you can feel. It's always fun to look at the body. A person's back is very insensitive. And you take two fingers and put them into your friend's back. You should do this. You know, it's another one of these experiments you should do. Have them turn around and put two fingers there and say, how many fingers are there? And they'll say, one. And do it with one finger. Do it with three fingers. Hey, can't tell the difference. Because your back was not really designed as one of your main things to go around feeling things. You know your fingers were. So the nerves in your finger are really close together. And that may be why the fingers are glowing more here. But look at these fingers. There's something wrong with them. So this is just measuring the amount of heat being radiated. They are not getting as much blood as the other hand is. There's something wrong with these fingers. So this is, again, just infrared. Here's another infrared thing. Interesting that you really glow. And I don't know what these circles mean, but nice picture. Now, light is a wave. X-rays are a wave. Infrared is a wave. Sound is a wave. Why not image with sound? How would you do that? Well, you could illuminate it with sound, go, ee, and then look at the sound that's coming back. Now you could actually take a lens and focus the sound. It turns out that modern computers these days, it's better to make a hologram. Hologram for sounds are actually easier to do. So typically that's what they do. They make a hologram of the sound. We touched on holograms. I explained how they work, but not in great detail. You don't really have to know how they work other than they take the wave that's coming in, they respond to the wave. In a sense, they preserve that wave. So they measure the wave and they record it. And then if you want to know what it really looks like, you can shine a new sound wave on this hologram, and the wave will come out exactly the same as things were on the inside. You could also convert that into light in the computer to see the image. So here's what's called ultrasound, and it's done by taking a sound wave, putting it into the body, looking at what comes out, making a hologram. If you do this every 1/10 of a second, you can make a movie. And what it shows you is where the sound is bouncing. Now that may or may not be useful, less useful for the brain, which tends to be all full of fluid. But if there are big body cavities on the inside with little things in them wiggling around, then you can see the little thing wiggling around, and all you're doing is bouncing sound off, so it's not very damaging. So let's look at a little thing wiggling around inside a body cavity. So that, depending on your politics, is either a baby or a fetus wiggling around in there. When we had my children, that was just 23 years ago. The images were pathetic. Couldn't tell whether it was a girl or a boy. Well, I'm not sure you can tell here either, but you can tell. And these days, the ultrasound movies are just fantastic, and they use this to look for possible problems. So that's the ultrasound. Again, anything that's a wave can be imaged. Wave or particle, for that matter. So let's see. Is there anything else left here in my slideshow? I think we've just about done everything. Okay, enough for the computer. Quantum mechanics. Turn this thing on. Take a few minutes to warm up. Well, sometimes I call it quantum mechanics, sometimes I call it quantum physics. Quantum mechanics is not really a good name. That comes about from the fact that mechanics is one part of physics, where you talk about forces and masses and so on. And when quantum physics was first developed, it happened to be mostly the quantum of mechanical things. And then a short while after that, they started doing the quantum physics of waves. And that became far more important than the quantum physics of just objects. So I prefer using the term quantum physics, but now every now and then I'll slip and say quantum mechanics. This hit us by surprise around the end of the 1800s, the fact that there were several things that were really peculiar going on. And I'll talk a little bit about the history, but let me tell you, all you need to know about quantum physics is basically right here. Well, this is a little bit short. We'll spend a lot of time talking about each one. These are the key elements of quantum physics. This is what was discovered. These are basically the 4 or 5 main items from quantum physics, the most important of which is that things we call particles are actually waves, or maybe we should call them wave particles because they're not exactly like waves either. Waves are not exactly waves, they're particle waves. What is a particle wave? That's what quantum physics is. Once you know that every object, every wave, everything is really a particle wave, you have the essence of quantum physics. Everything else is in the details. But changing your mind to recognize this, sometimes it's called the particle wave duality. It just means that things really have some of the properties we used to associate with waves, some of the properties we used to associate with particles. They are neither. People call this a paradox. Is it a particle or is it a wave? That's neither. It's a particle wave. Sometimes, in some circumstances, the particle nature will be what you notice. Sometimes it's the wave nature, but it's not a particle or a wave. It's not sometimes one and sometimes the other. It is neither a particle nor a wave. It's a particle wave. Typically, you can draw the particle wave as a wave packet. That's why you used to think electrons were waves, because when they move, they tend to have all of their energy concentrated in a little packet. And so just as we had waves bouncing off the rope, looking like balls bouncing off the wall, particle waves bounce. They behave in many ways like particles. But they also behave like waves. They can interfere. That's how we know it's a wave. The same way we know light is a wave, because you get cancellation and reinforcing. Electrons, neutrons, protons, all of these things, we've done interference experiments. You could take an electron and you could actually divide it up to go along two paths and then come back together and interfere with itself. And this has been done. In fact, this is how DNA was discovered, by using, I guess that was X-rays. Okay, it was not electrons. Take it back. So this is the wave particle. Now, a couple other key features here of quantum physics. We're going to be going over each one of these in some detail. Let me skip the quantum leap for just a moment and talk about the energy relation and the related thing called the momentum relationship, but this is the one that we're going to focus on in this class. When you have a particle wave, it'll have a frequency. It may have several frequencies inside of it. But let's take a wave that really has primarily one frequency. It just oscillates so many times per second. That particle wave, if it disappears, for example, by being absorbed on a surface, or by giving all of its energy to an electron, or something like that, if that particle wave disappears, we kill the wave, the amount of energy that comes out is given by this equation. It depends on the frequency. This is a very strange equation. It says the energy doesn't depend on the amplitude of the wave, only on the frequency. How could that be? Doesn't a bigger wave have more energy? The modern interpretation of this is what we found is going on, is if you have a bigger wave, you will absorb more packets of energy. But it'll always be a multiple of this amount. This is very abstract and not easy for you to understand. And why is it important? The reason this stuff is important is because of lasers, laser printers, night vision, solar cells, digital cameras, transistors, microprocessors, superconductors, electron microscopes, remote sensing and spectral lines to identify who's doing the pollution out of that. All of these technologies are based on this. Almost all of high tech is based on this. Quantum physics is behind every one of these things and even more. Your microprocessors are really, they are designed based on the quantum physics of the so-called energy gap. I call this the quantum leap. That's related to the energy gap. Let me put down the energy gap as a separate thing here, although it's really closely related to the quantum leap. Your computers work on what are called integrated circuits, which are designed on the same principle as transistors that operate because of the energy gap and the quantum leap. Every one of you probably uses every day technology that's based on this quantum physics. So I'll get into this a little bit. We'll discover this. The quantum physics was first really discovered. Let's see if we can turn the lights out and see if this is showing up yet. Lights out. I want to look over here at the screen. We have some colors. What we have here is a tube full of mercury gas. Electricity is flowing through that mercury gas, causing the mercury gas to emit light. The light looks kind of white, as you can see here. It looks sort of whitish. White mercury light. Pretty bright. So there it is, white. But if we send it through a prism-like device, this is a diffraction grating, but it works the same as a prism, so that the light coming through this is then separated into its different colors. So we expect to get a rainbow of light. But over here, now we need the lights down even further. Dimmer, dimmer, dimmer. what we find is not a rainbow of light, but lines of light. These are called spectral lines. Why do we have lines of yellow, red, and over here, purple? And there's another dim green one here. And does someone see a red over here? I don't see the red. Okay. Not only that, but if we go into the ultraviolet, there's a line right here that you can't see. You see it? Let's see. Here it is. This is a fluorescent screen. You may not be able to see that at home. But this is a fluorescent screen that's glowing green because the fluorescent glows green when it's hit by ultraviolet. So there's that line right there. Come over here. Well, this one, I could barely see the purple there, but it makes the fluorescent screen really glow brightly. And so there's this ultraviolet one. But why are these lines? Why are there lines and nothing in between? This is because of the quantum leap. Regardless of what causes this. I mean, right now, I'm about to explain to you what causes it. But regardless of that, this is enormously useful. Why? Because someone can look at this, and after a little bit of experience, they would say, oh, a mercury tube. The light is coming from mercury. How do you know that? Because mercury gives this pattern. It's like a fingerprint. It's called a spectral fingerprint. The fact is, most chemicals give a unique spectral fingerprint when they emit light. They emit light when they are hot. If you look at gases coming up in a smokestack or out of the engine of that airplane, and you divide it into its different colors, you get these lines. You don't get a full rainbow. You get these lines. These lines tell you what the chemicals are. If you look at the sun, what you find is you get a lot of rainbow. You get the whole rainbow. But in addition to that, you get a few lines. Those few lines enable us to know what the sun is made out of. It wasn't that long ago that people figured we'd never know what the sun was made out of because it's too hot. We can't go close, make any measurements. But it emits these lines. Now, why are these lines? Well, actually, the reason they're lines, let's have the lights back on now. The reason they're lines is because we have the light going through a slit. See, here's the light. It's a narrow slit. And so because it's a narrow slit that's coming, why do we have a narrow slit? We could have a pinhole, and then you would see points of light. But if we make it a narrow slit, then the colors go up and down, easier to see. So by making it a slit, we made it easier. That's why these things come out as lines. And historically, that's why they were called spectral lines. These days, people do other kinds of experiments. They just have a little point spot. They still call them spectral lines. It's just a term that's been left over. But the interesting thing is that you don't get a whole rainbow. The reason you don't get a whole rainbow has to do with quantum physics. It has to do with the fact that in the atom, an electron in the atom, you'd think could have any energy it wanted. It can go faster, slower, in between. It turns out it can't. In the atom, because of the fact that an electron is a wave particle, because of that fact and because of interference, the energy in the atom can only have certain values. These are sometimes called the energy levels. Every atom has different energy levels. When an atom changes its energy level, when an electron goes from this level to that level, that's called the quantum leap. When it does that, it emits a particle wave of light with the energy difference. So an atom can only have certain levels in it. The electron cannot go in between. It can't gradually lose its energy. It loses its energy in a quantum leap. The light that comes out always has that energy difference. And for different atoms, that energy difference is a different number. It's a different frequency. That's why we see these lines. I haven't explained to you why is it that an atom has only certain allowed energy. I told you it's because it's a particle wave. Okay? For now, until Thursday, that's all you need to know. Well, you do your reading for Thursday. It's a particle wave that causes the atom to have quantized energy levels When the electron makes its quantum leap, it emits light that has the exact energy difference between those. And that exact energy difference, what we're seeing here are the list of quantum leaps that you can have in the mercury atom. On Thursday, I'll tell you why.